Seeking English, S.A.T. Workbook, page 342, problem 4. There's a lot of words. Amanda has a 1-gallon pitcher that she plans to use for serving cold drinks during a party. How large is a gallon? We're going to find out. She fills the pitcher with 75 cubic inches of ice. But teacher, I can't do that with a gallon. Okay, we'll get there. 75 cubic inches of ice, then pours in soda from as many individual cans as possible. Okay, meaning she's probably going to stop when that next can is not going to fit. If each soda can is in the shape of a right circular cylinder with an internal diameter of 3 inches and a height of 5 inches, how many full soda cans can she pour into the pitcher without it overflowing? So yeah, she wants to stop before she opens that last can that's not going to fit. It says, note, there are 231 cubic inches in 1 gallon, which is what you needed at the beginning of the process. And you may have found yourself distracted from the rest of the thing, thinking, what am I going to do with that gallon? Okay, so yeah, if you find yourself reading it again, don't feel bad. That's probably normal. Okay, but other than that, the chronology is reasonably clear. You have a pitcher that has some space displaced, so it has a reduced available volume, and you have some cans that have some volume. And if you take that available space and you divide it by the available volume, or the fluid that's in the can, you get an abstract number of cans that needs to be rounded downward to a whole number to get any of these answers. The answers are 2 cans, 3 cans, 4 cans, and you'll notice they don't have 5 cans, they have 6 cans. That gap is interesting to me in terms of how the number pi relates to this problem. I'm probably not going to do that in this video. Okay. Says 231 cubic inches minus the 75 inches displaced by the ice. From there, okay, you need to divide that by the volume of 1 can to get the number of cans. Okay, so the formula is there's the height of the cylinder. Okay, there's the height, and there's the diameter they gave you, and they did not give you the radius, which is going to be half that, and that's one of the risks in this problem. Okay. So it's going to be the height, okay, and then it's going to be the radius squared times pi. And if you see these elements in some other order and some other problem, that's fine. I just like having the rational numbers close together and having the irrational number out on the edge. It's my own preference. Okay, so if it says the diameter is 3, then the radius should be 1.5. Okay, so if you did not have a calculator, I would suggest maybe doing it like this. Okay, doing that. That's the diameter cut in half to give you the radius. If you square that, it becomes 9/4. Great. Okay. You're not going to do that because in this problem, you probably do want to use a calculator at the end of the process with pi. If for some reason your calculator doesn't work, in this case, in this specific instance, there are reasons in this problem why you could actually plug in 3 for pi, but don't do it. Let's pretend you're going to use a calculator first, okay? It's going to become 1.5, okay, squared. We know that height is 5, okay? So we have this pi here, which is an irrational number, but it's a number. And we have this other number, and we have this other number. So from there, we should be able to calculate. 231 minus 75 should be 156. If it's not, I'm going to have to do this video again. 156. From there should be 2.25 times 5. That should be 11. Sorry, is it 11 point? What did I say? 2.25 times 5. Yeah, should be 11.25. I think so. Okay, now here, what to do with your calculator? It's not everyone does things this way. My scientific training says if you have an irrational number in the process, you put off as long as possible dealing with that to maximize your. So when you account for rigor, or when you have to round things, that you have gotten them as precise as possible. if you put in pi at the beginning of the process and you start playing with it, the limits of your calculator will start causing pi to deteriorate further than what you've already put in. I know on the S.A.T, why does it matter? If you're not dealing with bizarre scientific numbers that are really complex, it probably doesn't matter. But my scientific training says try to deal with pi last, which means I'm going to divide 156 by 11.25. And then if I'm not going to multiply by pi, pi's on the bottom. I'm actually going to divide by pi at the end there. Divide 156, which is a rational number, by another rational number. I reduce that as much as possible, then I'm going to hit pi. What does it matter on the S.A.T? Not in this case, and like I said before in this problem, the difference between 3 and pi actually wouldn't matter in this problem. And I might make a separate video detailing why that might also be helpful on some other problem. But this time I think I better just finish up. So calculator, just following the procedure, is 156 divided by 11.25. Equals 13.86 repeating, and then I'm going to divide that again because, as you can see, pi is in the denominator. Divided by, I'm going to say 3.14 just because this calculator doesn't have a pi button, oddly enough. And that's going to be more than close enough. Equals 4.4161, whatever it is. What you need to know is, even if it were larger than 4.5, you do not want to round to 6, and they've actually made this easy for you by not giving you a 5 to round it for if you somehow get off a little bit and get above 4.45. So I could include a couple of elements to this problem to make it a lot more complicated. They did not include it. It would be very easy to include them. Dropping letter D down to the number 5 and giving you some kind of a calculation that bumps you up before. Okay, I'm going too far with this. So the correct answer, if it is anything less than 5, really if it's anything less than 6, in this case, it's going to be 4. Okay, that's it. 4 point something becomes 4. You're going to put 4 cans in there. It's an awfully long explanation. If you are interested in the even more complex explanation of how to attack this problem more quickly and brutally for exactly the same result, if you can get it, please tell me in the comment section. I'll make another video specifically about this problem, which from a scientific standpoint is amusing.